everybody, welcome to section 4.5. I hope it's been going well. What we want to focus on is graphing logarithmic equations. The way the textbook does it is it has you use the change of base formula and plug it into some type of graphing utility. I just find it helpful to graph logarithmic equations by hand just so I can continue to attain more comfort with them. So here is a suggestion of just how I graph them. First off, when we're looking at logarithmic equations, you still have the same rules of transformations that we learned in section 1.5. And one of the things that I find helpful in graphing logarithmic equations is to begin by stating the domain. And to find the domain of a logarithmic equation, you want the argument to be greater than 0. So we would set bx plus c greater than 0 and solve for x. And then, I'm not going to necessarily do this nasty example. We'll do something a little similar in the next problem. But I just want to start by graphing y equals log base 2 of x. There's a few approaches you can use for this to graph these. This is just the one that I found the most helpful. And so the way I'm going to do this is I'm going to convert my logarithm to an exponential. So this would be 2 to the y is equal to x. And what this is telling me now is if I give u and y value, I'll be able to get the x value. So I'm going to use that to my advantage and make a table. And so I'm going to get some ordered pairs. So maybe -1, 0, and 1. Because after all, this is just an exponential in terms of y. So when I when I graph this, when I plot these points and I evaluate these points, I'll get 1/2, 1, and 2. And so you should be thinking, oh my goodness, this is similar to exponentials, and it is. One of the biggies of inverses is that you switch your x and y coordinates, and so essentially that's kind of what I'm doing with this logarithmic equation. And so when we graph this, I still have my vertical asymptote, and when you plot 1, 0, you'll be here, 1/2, -1, and then 2, 1. So the curve's doing something like this. And just in terms of the exponentials, right? If this is y equals log base 2 of x. It's an inverse function would be y equals 2 to the x. So when you plug in 0, you're going to get 1. When you plug in 1, you're going to get 2. And when you plug in -1, you'll get 1/2. So here's our exponential function. And what we've learned through our study of inverses is that the function and its inverse is symmetric across the line y equals x. So what we did to graph this logarithm was convert it to the exponential, plug in values for y, and just directly plot that logarithmic equation. Alright, so let's look at a different example. Suppose we had y equals log base 1/3 of x plus 1 minus 2. So the way that I'm going to think about this is I'm just going to look at this function as y equals log base 1/3 of x. I want to find those nice points that I have here, right? And then apply the proper transformations that we know about. So in order to graph this, I need to convert this to an exponential. This would be 1/3 all of it in parentheses to the y equaling x. So this means that when I plug in numbers for y, I'm going to get x. So the numbers I like to plug in are -1, 0, and 1. And so when I plug in -1, I'm going to get 3. When I plug in 0, I'm going to get 1. And when I plug in 1, I will get 1/3. And so what this is now telling me is I need to subtract 1 to all the x coordinates, and I need to subtract 2 to all the y coordinates, and that's going to get me the graph of my y equals log base 1/3 of x plus 1. So when I do that, it's going to, maybe I can squeeze this in here, so I'm going to -1, -1, -1, and then -2, -2, and -2. So essentially what we are graphing is getting the ordered pairs for the function that we need. So 3 minus 1 is 2, 1 minus 1 is 0, and 1/3 minus 1 is -2/3. And then -1 minus 2 is -3, 0 minus 2 is -2, and 1 minus 2 is -1. I did forget to state the domain. The domain is everything greater than -1, because I set x plus 1 to be greater than 0. And so let's go to a new page, and we'll go ahead and plot these points. You have your vertical asymptote, and we have 2, -3, and the other one was 0, -2, and the last one is -2/3, -1. -2/3, -1. Oops, I'm off. I gotta go downward. -2/3, -1. And so the graph of this is going to be, whoop. And so hopefully you're convinced of this. Let's see, we ended up graphing y equals log base 1/3 of x plus 1 minus 2. And what you should realize is that if we were to convert this to an exponential to find the inverse function for this and plot that those would be symmetric over the line y equals x. So I'm going to leave that to you to verify. Another thing to note too is just from this example, when the bases are greater than 1, similarly here too, you have exponential growth and the logarithmic's growing. When we have the bases 1/3, right? If it was an exponential, it's decaying, right? And so if you were to flip that over the flip this over the line y equals x, it's going to come this way. So you can still see that those are mirror images across the line y equals x. So hopefully that's convincing you a little bit more. Alright, so I hope you found this helpful and can get a better understanding of logarithmic equations.